Hi, welcome to the Signal Path. I have another product review for you guys and I'm really excited about this one. This is the Keysight MSO-S Series 10-bit oscilloscope. It's an 8 GHz model with 20 gigasample per second on 2 channels, a really capable instrument. And Keysight claims to have record low noise and very high spirit-free dynamic range and very high ENOP from this instrument, and a whole slew of different kind of application that it supports. So what I'm going to do is, and I'm not just going to show you what it does, but you're going to have to set up some experiments. We're also going to do a teardown of the acquisition board and take a look at it. So it's going to be a really exciting review. So it's broken up into a couple of different sections. So first we'll do the overview and the teardown, then there's going to be some performance verification, and then there's two different types of application, one wireless application and one broadband backplane type of application. So make sure you watch the whole video through. There's a lot that I want to say, and make sure you let me know what you think about it. Well, look what I have here. This is the acquisition board for the S Series oscilloscope from Keysight. And no, this is not the one from the scope that's sitting on my bench. This is a separate one that I borrowed from Keysight so I can show you the internal construction of this scope. And I thought it would be more interesting for me to tell you about the architecture and the different components that sit on this board and tell you about the performance of various elements that are here, which ultimately lead to the world-class performance that the S Series oscilloscopes from Keysight actually have, because there are some really amazing components and architectural decisions that have been made for this board to come together. And as you can see, it's really complicated. And it's very, very interesting because it is an entirely self-contained unit. The only interface this board has to the outside world, basically to the internal PC that's sitting inside the S Series scope, is through a PCI Express line. There is no other connection between this board and the PC. So all the massive processing of the data, of the hundreds of gigabits of data that come from the A to D converter on this board is fully processed here. All the memory is dedicated here, all the FPGAs that do all the filtering and triggering, everything is on this board. So the PC doesn't do anything other than displaying the final image that is responsible for showing you the graphs and so on. Even though the scope is really fast, all the processing is handled here. And that's a really important thing. That's one of the reasons why it is so fast and one of the reasons why you can access the internal storage memory so quickly. And the only other interface is of course the power, but this is the only way you can get information in and out of this scope. I thought that's really cool, a really interesting and smart decision. And I also want to show you the architecture of this, and in fact I have the block diagram. So let's go over the block diagram quickly. It's a very simple one, and then we can go over various components and I'll tell you more about them. So here's a very simplified block diagram of the entire oscilloscope system. It has different elements and components to it. It has the assembly of the keyboard, which has its own FPGA and LED drivers and so on. Not too interesting for us at the moment. But here's the entire motherboard where the PC is there, the Core i7 Intel processor, the SSD hard drive, the 8 GB of RAM, and all the other wonderful things that go into a typical PC in a very, very fast scope like this one. The board that we were looking at is this acquisition board right here. And as with any 4-channel oscilloscope, you of course have 4 inputs that go into 4 preamps. Now these are not just any preamp, because these preamps have to support 8 GHz and they have to be really low noise in order for them to be able to serve a 10-bit analog to digital converter. And the data from all the 4 preamps go into a single analog to digital converter. This is a little bit different too, because typically if you're used to seeing perhaps 2 ADCs, where each ADC serves 2 channels of the scope. In this case, there is only a single ADC, and I want to talk about that separately and tell you more about it, because it is a world-class analog to digital converter on this scope. There's also the entire component for the digital channel controller, which controls the MSO, the 16-bit of the digital lines that can come in. There's a time base in there, an extremely remarkably impressive time base for a scope like this, and I'll talk about that separately. And there's a whole bunch of FPGAs scattered all around this board doing things like the triggering, handling the trigger events, handling all the memory I/O right into the really fast memory, doing filtering and conditioning the signals that come directly come out of the analog to digital converter, and we'll talk about that separately too. So the architecture on first glance is really simple. Signal comes in, gets digitized, goes in the trigger IC, gets written into the memory controllers, and so on. So pretty straightforward. Let's go ahead and take a look at each of these individually and see why they're so special. So now we can compare this with the block diagram we just looked at. So here are 4 input channels. This one I have removed the protective can so we can take a look at what's underneath the input channel. The SMA connectors are directly underneath these, and I'll flip this board around and show it to you afterwards. So here are 4 channels. The signals come together going to our analog to digital converter. The trigger FPGAs and the memory is right here. Here's another FPGA here which handles all the filtering and giving you a really nice flat response. All the calibration coefficients of all the channels are in here, and this is processed live as the data comes through it. Very interesting. And I believe it also might be connected to the PCI Express. If not, this is the main FPGA of the board itself which handles the PCI Express communication as well. And right here is where the digital MSO inputs come in, so they also go through that FPGA too, and there's some extra memory here. There's a massive amount of memory underneath this heatsink, and I'll flip it to the other side so we can take a look. But let's go ahead and take it one step at a time. Let's talk about the 10-bit analog to digital converter because it is a world-class performance component. Now, because the heatsink is really stuck to the component, I didn't want to remove it because I wasn't sure what plans they might have with this board. But instead, I have a picture of the packaged ADC here so we can take a look at it. So as you can see immediately that this is a system in a package architecture. It's a BGA, so all the bumps are underneath this. But there is 2 flip chip silicons on top of this. This big piece, you see that right here, is a flip chip 65 nanometer, 40 gigasample per second ADC. The ADC itself is a world-class performance. There is no other 10-bit 40 gigasample per second ADC in the world. This is the fastest one, as far as I know at least. And this one is in 65 nanometer CMOS. So you may ask, well, what is the point of this? Well, if you think about it, the architecture of the ADC itself is a 4 by 10 gigasample per second. So they have 4 10 gigasample per second 10-bit ADCs in here. Each of those 10 gigasample per second ADCs themselves are time interleaved, and you can time interleave the 4 by 10 to get 40. But what I believe they have done is that this is a front end. This front end is actually in 0.13 micron SiGe by CMOS technology. And because the dynamic range of the HBTs is so much more than the 65 nanometer SiGe by CMOS, typically you can make really good front end to ADCs using this. In fact, this is one of the things that I did in my thesis. Back when I made millimeter wave ADCs. But anyhow, so what I think they have, I don't exactly know what components they have put in the 0.1 micron SiGe by CMOS here, but what I suspect is happening is that perhaps the track channel amplifiers and the switching matrix, which allows you to route the signal to each of the 4 by 10 gigasample per second ADCs, are in fact contained in this component. So the front end THA as well as the time interleaving components that allow this to act like a 40 gigasample per second ADC is contained in here. So this dual chip architecture in the same package is common, taking advantage of the high dynamic range of the SiGe combined with the high levels of integration and calibration capability of CMOS in here to make a really world record performance analog to digital converter. So this is why this scope is able to do what it does. It's because it's the only one that does have a real hardware 10-bit A to D in it and does not just rely on oversampling to achieve higher bits. Of course, you can still do this, and this scope can give you 12 bits if you were to do high oversampling as well. So it can work as a 12-bit A to D in high resolution mode or a real 10-bit hardware ADC in regular mode. So that's why this ADC is so special, and we can talk more about it, but I thought it would be interesting to tell you more details of how it works. And the performance of the ADC itself is also really good. It has an ENOB of 8.7, but of course the ENOB of the ADC itself is not the only thing that matters. You want the system ENOB, and the system ENOB depends on many other factors. That includes the linearity and the noise of the front end, as well as the quality of the time base. And this scope achieves an ENOB of better than 8 bits up to 1 gigahertz, and better than 7 bits up to about 5 or 6 gigahertz, which is really impressive. It may not sound like much, but going from 6 to 7 bits is not the same as going from 7 to 8 bits. The problem gets exponentially more difficult, and you want a really high ENOB ADC as a system performance, not just the ADC by itself, because you don't want, of course, your oscilloscope to be the limiting factor when you're doing sensitive linearity measurements and SFDR measurements. You want the scope to essentially be invisible. So these are really amazing numbers considering that this scope has 8 gigahertz of bandwidth. And I'm very impressed with it, and hopefully, and I think that they're going to have some fun with this scope and do some other pretty cool stuff with it in the future, I'm sure. But so, enough about the ADC itself. Let's look at the front end a little bit. So here's a closer look at the analog front end of the scope itself. On the other side of this board is the SMA connector before it is fed into the front end here. And one of the nice things about this scope is that it also supports a 1 mega ohm input up to 500 megahertz. So you can actually use it with a passive probe up to 500 meg. You're not stuck in a 50 ohm impedance. On top of that, it can provide up to 8 gigahertz of bandwidth in a 50 ohm environment, which is really nice. I like the fact that they didn't get rid of the 1 mega ohm input. And the signal, after going through relays and so on and on, I don't want to talk too much about that, it goes into the ASIC that's designed by Keysight, which is the main front-end analog processor for each of the channels. And you can see that here is a single-ended input, which is a coplanar line here going into this, and it seems like it comes out as a differential microstrip line. It could be a combination of a microstrip and a coplanar, I'm not sure here, but then it goes into the ADC, so it does things into the differential conversion also. Some of the things that are special about this ASIC is that it actually supports 2 millivolt per division in hardware, so it has to be very low noise in order to be able to support that. And its noise is very, very low, and I don't want to give away exactly how much because I want to show it to you on the scope, because it's actually quite striking when you see it. But I will tell you that it does have a spurious free dynamic range of better than 73 dB, which is again really, really impressive. And you need that if you're going to couple that into a 10-bit A to D converter, and of course it has 8 gigahertz of bandwidth. So this is one of the reasons why you are able to get such a high performance from the whole system as opposed to just from the ADC. The worst thing you want to do is you can have an excellent 10-bit ADC with a really terrible front end, which of course then defeats the purpose. So when you're looking at specification, you have to look at the system noise performance as well as the system jitter performance before you make a decision on what is good and what is bad. And this is what they're focused on, and I want to talk about that next. So here go, take a closer look at this here, and I'm gonna have to flip the board on the other side so you can see it, but first let me get to the other part. But yeah, the one of the other really interesting thing about the analog front end of this is that because this is a fully custom part they've designed, they also have the firmware in order for you to select which bandwidth you want. So all the bandwidth handling, aside from some hardware bandwidth limitation, is set in here, and a whole bunch of other processing is done in one of the FPGAs in order for you to get a really good flat frequency response. So because they don't want to do all of the processing of the bandwidth just from the front end, they actually have a dedicated bunch of filters that run in real time, doing the calibration, doing the filter bandwidth adjustment all in real time. And let me show you a plot here that demonstrates that point. So here's the 8 gigahertz version of this scope, and if you take a look how flat this bandwidth response of the whole system is. It's quite amazing. This is you can see that this is plus 1 dB, this is minus 1 dB, and we're looking at 8 gigahertz, we're only half a dB down. So this 8 gigahertz model of the scope does not have a 3 dB bandwidth of 8 gigahertz. It has a half a dB bandwidth of 8 gigahertz, which is really amazing. And this flatness here is accomplished, of course, with calibration at the time when you purchase the scope, and is programmed into the FPGA. So if you change the bandwidth from 8 gigahertz, let's say to 6 gigahertz, it's going to give you another brick wall filter. So let me show you that. Here's an example of when the scope is set to 6 gigahertz. And look at that. You get just a brick wall filter at 6 gigahertz. By the time you're at 6.1 gigahertz, you're already 7 dB down, and of course you maintain the flatness. And they do this for every single bandwidth that you select the scope to be. So a combination of hardware and software bandwidth selection gives you a really good flat response. If you don't have a flat response and a good phase response from your oscilloscope itself, then making eye diagram measurements becomes quite difficult and quite annoying, because you don't know, is it the channel that's limiting my eye diagram? Is the shape of the eye diagram a result of the scope measurement or the result of my circuit? And this ensures that your scope is essentially invisible as far as your measurements are concerned. The next difficult piece of the puzzle is the time base of the entire oscilloscope. And what they've done here is they have exceeded expectations by a long shot. They have designed a time base that's accurate to plus or minus 12 parts per billion. That's billion with a B, not million. So it is an extraordinary time base they've done. That's after, of course, their own internal calibration and all that. And it is based on an oven-controlled crystal oscillator coupled with a Crystek VCO here that you can see, at least two, and of course their own PLL and so on. And because they've chosen such high-quality components and they do their calibration and they have a very, very good PLL, the jitter floor of this instrument is only 100 femtosecond. And you may ask, why did they go through so much trouble making such an incredibly low accuracy time base. And this is because even though the scope ships with 50 million points per channel, so that's 50 megapoints per channel of standard memory, it is upgradable to 400 million points per channel. And if you're going to capture such an incredibly long sequence of data, you better make sure that you have a really high precision time base, because you don't want your time base to drift during your capture, and it will when your memory depth is so high. So what they've done is that they've made sure that the accuracy is very high and the jitter is very low, so that your data, once you capture 400 million points of data, the first edge of your data and the last edge of your data haven't drifted with respect to each other because of the jitter. Otherwise, you don't know if you're measuring the signal into the circuit or you're measuring the jitter of the scope itself. And I will do tests on all of these things so we can play around with them, but that's really the philosophy behind it. You want to make sure everything they've done here, from the A to D itself, from the low noise front end, from the time base, is to ensure that when you do your measurements, you're not measuring the scope, you're measuring your signal. And that is the best thing you would ever want to receive from any instrument that you have. You want to make sure that all your measurements are the measurements of your circuit. So let's go ahead. I'm going to go ahead and, sorry, I'm going to shift this over here and flip the board so you can see the other side of it. Oh, and before I do, by the way, this is the scope actually does this entire triggering, I believe, all in the digital domain. So it has a digital triggering system which is handled by these FPGAs themselves. And these FPGAs also read and write to the memory and can handle every single memory transaction that has to happen extremely fast, so that the PC doesn't do any of that. And there's a direct driver that then writes to the screen directly from the memory, and is all handled through these FPGAs, which making the update rate to be extremely fast and responsive. And when you have 400 million points per channel of memory, you want to be able to access them really quickly and jump back and forth. And you can segment this to like 65,000 segments and so on. It's just crazy what you can do with this. So let me go ahead and just flip this over without banging it around too much. Here we go. And you can see a little bit more clearly. So there you go. You can show you there's a memory, of course, at the back of the unit here too. Look at that. And there's, they've taken the heatsink off here. There is a nice shot there for you to see all the massive amount of memory, 400 million points per channel, just crazy. And then you can see all the back of all the FPGAs and all the components that are there. A little bit more detail here on the input. And these BNCs are not typical BNCs, of course, because a typical BNC doesn't have 8 gigahertz of bandwidth. So these are specially designed BNCs in order to have the handle all the high bandwidth that is required for these. And here's some memory again for the digital inputs. The back of the board is fairly empty. It has a whole bunch of other components to handle the power and so on. You can see that this must be a reasonably early version of the board, because there's some fixes and things that they've done on it. But it looks really nice. This is, I think this either maybe a 24 layer board, but man, it's also really heavy, because it's all made with all the shielding and everything is quite heavy on this board. And here's all the other interfaces, the 10 megahertz in and out, and the triggering and so on. But there it is. Take a close look at it and see what it can do. And again, the filtering that I showed you earlier, the really brick wall filtering, is done partially in this FPGA, aside from some of them that's done in analog. The only component that I'm not 100% sure what it is whatever is underneath this fan here. I don't exactly know what that does. Could be part of the clocking scheme, because I don't believe the PLL generates, of course, the signal directly at 10 gigahertz that's required by the ADCs at a much lower frequency. So there is some other stuff happening somewhere else. But I think I don't want to talk too much more about this. I'm sure you're all eager for me to turn it on and actually play with it and do some real tests, some real life situation experiments which I have prepared. But pretty amazing. So let's go ahead. Well, here we are. Now, before I do anything, I wanted to show you the upgradability of this scope. As I mentioned before, the Keysight MSO-S Series is fully upgradable from the base unit to the highest possible configurable performance, both in terms of its bandwidth as well as its memory and all the other applications that can run on it. So if I go ahead right now and look at under help and about, let me see if I can focus in here a little bit better. You can see that the model number is listed as the MSO MSO-S 104A, which is the entry MSO level, and I've updated the latest revision of the software, and you can see that under install options, this is what this scope originally came in, and it's got the app remote and the noise reduction options already installed, which are the basic units that come with it, as well as the fact that it has the MSO, which means that the digital inputs at the front are enabled. But just to show you how easy it is to upgrade the scope to the highest possible configuration, I'm just going to go ahead and exit the software here and go yes, and then that's going to take us directly on to, of course, the Windows environment. This is running Windows 7, and if I go ahead and plug in a USB key that has the appropriate license on it, so I have this USB key that has all the licenses possible available that Keysight has kindly sent me, and you can see a little bit of my reflection in the screen. The screen may look very reflective on the camera, but actually it's not, but for some reason, because of the angle of the camera, you can see my image in there. So let's go ahead, and I'm going to go ahead and plug this in to the front. There we go. And there it is. I actually did everything by itself. I didn't even have to do anything. And you can see here the license manager, the Keysight license manager, has automatically discovered that there was a license file in there and the version number and everything, and automatically applied all the licenses. So if I now go ahead and open the license manager, you will see that there it is. All the licenses. It's got a permanent license and the unlimited, on this particular host ID, and you can see that we have the bandwidth, the demo, and the MSO, and all that stuff. All the functionality has already been installed. So what does that mean? So now if I go ahead and close the license manager, and once again launch the scope software itself, here we go, which is going to run, of course, this software will load all the toolboxes, as well as check some internal self-check of the scope as it boots up, and you can see that it's booting up all the different apps on there. And of course, because this is a Windows machine, you can close and open the Infinium app anywhere, anytime you want. There you go. It just did a self-test, and it's initiating the probes, and it will boot up in just a second. There it is. Here we go. So now you can see that if I go under Help and About, now we have everything you would ever want. Look at that. It's just a list of applications, just keeps going. You can see there is a lot of things you can do, of course, with this scope. Now the license key that I have just simply enables every possible application. You wouldn't want to buy every possible application. It would be very expensive. You would buy them as your needs are requiring, the different types of analysis if you're working on 10G networks. And you can see here are the interesting things that are of relevance in a 1G upgrade, 2.5 G. This is the bandwidth. 2.5 gigahertz upgrade is 200 million points of memory upgrade, then 2 gig, then 400 million points. Then there's the Ethernet, and then finally 500 million points, and then 6 gig and 8 gig upgrade. So with that, the scope now has the highest bandwidth and the highest memory and all the applications and everything that you could possibly do with it. And you can see how straightforward and how easy it is to upgrade this scope. This is a huge advantage, of course, because when you go ahead and purchase this scope first, you may not have the funds or the application that requires a particular type of bandwidth or type of analysis software on it that you may not need right away, and you can do that later, and you don't have to make a decision. And even more importantly, you don't have to send the unit back. It's fully upgradable, which is really important from a testing perspective, because you don't want to lose any time sending the scope back to Agilent or to Keysight, for them to upgrade it. So now you don't have to do that, and you can completely upgrade. Now the only thing that's left is to go ahead and apply the new sticker, which is now going to say the Keysight MSO-S 804A, which is the highest, 8 gigahertz, 20 gigasamples per second model number, as opposed to what's already there, which describes it as the MSO-S 104A. So with the sticker, not necessary, of course. The sticker doesn't do anything. It's just aesthetics, but it's nice to have, and they've been kind enough to send me one. So there you go. So I'm going to go ahead and apply this, and then we can take a look at the scope itself. There you go. Now that you saw the upgradability of the scope, now we have the Keysight MSO-S 804A here in the lab, so I'm going to power it on so you can also see it boot up. Just as a side information, the PC that's inside this unit is a quad-core i5 processor running at 3 GHz. It has 8 GB of RAM, and it has a solid-state hard drive running Windows 7, so it's really quick. The solid-state drive is very beneficial, not just for the boot up, but when you want to put a lot of data in and out of the hard drive, especially with the expanded 400 million points of memory per channel, you would want to have a really fast SSD hard drive if you want to save files and so on. So it can be really beneficial. It has 6 USB ports, it has USB 3.0, it has a gigabit Ethernet, it has and also as well as a display port and VGA output, and it supports multi-display, so you can have this display as well as another one. In fact, I've connected it to another display on the side, which I will show you. And before I tell you a little bit about the interface, let's go ahead and power it on and also time how long it takes for it to power on. Here we go. So it has a soft power on button, of course, and you can see in the front panel we have the 4 analog inputs with the Pro power connectors in there, which of course support a whole variety of different Keysight probing systems, and I'll show you some of the ones that I have. Here's the digital inputs right in the front panel, nice and convenient. The probe compensation is also right here. 2 of the USB ports are in the front, and one of them right now is occupied with a wireless mouse and keyboard so that I can use it in the Windows environment and also with the interface itself. Now on the right side, the main interface of the scope, it uses these really flat buttons, the really modern style that Keysight has adopted. I like those. You don't accidentally push any of the buttons. It has a really nice flat look to it, and I like the interface. And what I also really appreciate is that they've gone ahead and they made sure that they only put buttons here that are absolutely necessary. There is no junk button that you would never ever use. And just one moment, I'm going to make sure I time this when it gets to the there you go, it's now ready. So it took exactly 1 minute. So in 1 minute the whole scope is up. Remember, that's really impressive for the whole Windows boot up as well as the software to launch and the soft test to run and everything, and now it's ready to go. Anyhow, so back to what I was saying here, each channel has its own individual vertical as well as the vertical scaling as well as a vertical position, and you can enable and disable each channel individually, of course. All these support push for vernier or for zeroing them and so on. And then the top of the panel is divided into multiple sections. So you have the main run control, and then you have all the horizontal settings you would want to access, all the trigger settings and all the measurement settings. They've gone into trouble making sure that they only put the buttons you want to use. So there's nothing here that you wouldn't normally or repeatedly want to have to access. So I appreciate that they haven't flooded it with buttons that I would never use. And the trigger interface here, I love that. The fact that it tells you what trigger you're doing. These little details make a big difference when your head is filled with the measurement you're trying to do and you don't want to have any distraction of figuring out your instrument. So I really like the interface. Of course, the buttons feel really nice, the knobs are fantastic. No questions, no complaints there. Now, if you remember, when I was showing you that in the details of the inside of the acquisition board, there was one little detail I didn't tell you. I didn't tell you what the noise was because I wanted to show you how incredibly low noise the front end of this scope actually is. One other detail is that this is a fully touchscreen multi-touch display, and you can move waveforms in and pan to zoom in and out and all the fantastic things you can do with a multi-touch display, including the fact that they have optimized this GUI to make sure that it is touch friendly. Now, for most of this video, I will not touch the screen because I don't want to continuously bring my hand in front of the display while you guys are looking at it. Instead, I'm going to use a keyboard and a mouse interface right now, which you can, I can just move the mouse very easily. So on this, I do this simply because I don't want to have my hand in front of it, but otherwise it works really well that the touch screen is optimized and so on. The only complaint I have about the display is that the resolution of the display is 1024 by 768, and it's a little bit low because the reason for that is not because Agilent didn't want to put a better one in there, or Keysight didn't want to put a better display in the unit, is because the industrial grade of this display with the touch screen and the thick glass and so on, which is industrial grade, hasn't caught up with the resolution of typical displays that you see in a computer monitor and so on. That's one of the reasons. There's industrial challenges with putting something like this in an instrument, and that's one of the reasons behind it. But if you connect it to an external display with a display driver, then you can go very high resolution indeed without any issues. You won't have a touch screen anymore, but if you're using a mouse and a keyboard, it doesn't matter. Anyway, so let's go ahead and look at the noise of the Keysight MSO-S series. Now, one of the unique features of this scope is that it gives you the combination of high resolution as well as high bandwidth. all the other competitive products, all the other HD scopes that are on the market rely on oversampling, and as a result, because the sampling rate of the ADC, analog to digital converter, is limited, they have to limit the bandwidth in order to get high resolution. That's one of the reasons why I really like this scope, because it does give me 8 GHz as well as a 10-bit ADC. On top of that, I can of course do the traditional oversampling, and in fact it does that when you tell it to have a high resolution mode. In that case, the bandwidth is then automatically limited to a much lower value in order for you to get 12 bits or more. So in order to have a fair comparison with the other scopes that are on the market, I'm going to go ahead and reduce the bandwidth of this scope to 1 GHz via the acquisition menu, and then we can measure the noise of a 1 GHz front-end portion of this scope, and then we can do some comparison. So let me go ahead and zoom in a little bit here. So in order to do that, we can go ahead under Setup and under Acquisition. And here we can go ahead and here you can control the entire acquisition system of the scope. You can tell it to do real-time, equivalent time, segmented, and all the other kind of roll mode type of sampling that you would typically expect from an oscilloscope. But you can also change the bandwidth. You can change the depth of the memory as well as the sampling rate. So I'm going to change the bandwidth from automatic to manual, and then this allows me to have 500 megahertz steps of bandwidth adjustment. And remember that this bandwidth adjustment is accomplished not just in software but also in hardware, and it's done in a DSP and an FPGA, so it's really fast and real time. It's not done by the computer, it's done by the FPGA, so there is no change in the acquisition waveform speed by doing this. So let's go ahead and go down all the way to 1 gigahertz. Here we go, 1 gigahertz, and I'm going to change the depth of the memory. I'm going to make it 1 million points. Remember, I can go to 400 million points per channel, but 1 million is enough for my purposes here. And that's it. I'm going to keep everything the same. Remember, the sample speed stays at 20 gigasample per second. Let's close that, and in order to have a consistent measurement, I'm going to also go ahead and change the horizontal range to 1 microsecond per division. There we go. So now we can see at the bottom here we have a 1 microsecond per division range, and I'm going to now go ahead and change the vertical scaling, and you can see the noise. There we go. Right now we are at 1 volt per division. Let's go ahead and change that. 500, 200, and 1 millivolt per division. This is a 1 millivolt per division scale right now with a 1 gigahertz sampling, 1 gigahertz bandwidth and 20 gigasamples per second. Look at this noise. It almost doesn't look real. How little noise there is, where this distance here is 1 millivolt, this distance here is 1 millivolt. Whoever said analog scopes are less noisy should come and take a look at this. This is quite an accomplishment. In fact, the lowest front-end noise in the industry, and remember this also supports all the way up to 8 gigahertz. Of course, if I change the bandwidth to 8 gigahertz, the noise will grow because the noise is distributed along the entire bandwidth. But when you limit it to 1 gigahertz for very high resolution work, it is absolutely amazing. Let's go ahead and do some measurement on this. I can go setup, I can go under measure and I can add a measurement. So let's go ahead. Under vertical, again, you can see how the menus are, everything is quite large because it's supposed to be touch friendly, but very easy to use nonetheless. So there you go, RMS. I'm going to go ahead and add an RMS measurement. I'm also going to add a peak-to-peak value measurement. Now, the peak-to-peak value, you have to be careful here because this peak-to-peak now applies to the way I've set up the scope. That's why I had to set the memory and the time horizontal resolution to a specific value so we can have a consistent measurement. I'm going to go ahead and apply that as well. And take a look at this number and tell me if you've ever seen such a low noise front end from a scope. Look at that. The RMS noise of the front end is about 87 microvolts. So here's the mean. There you go, 86.9 microvolt RMS with a peak-to-peak value of 732 microvolt within this window of capture. This is an incredibly low noise value that they have accomplished. Now remember that this front end would have been easier to design if it was only limited to 1 gigahertz, but it's not. It can also have a much higher capture rate, and that's the beauty of this. It gives you the combination of noise and bandwidth. So if I go ahead and increase the capture bandwidth to something higher, the noise will of course be expected to go a little bit higher. So let's go ahead and again go under setup and acquisition, and I'm going to now go ahead and change the bandwidth from 1 gigahertz. Let's go 5 times larger and 5 gigahertz. Now we have a 5 GHz capture, same vertical scaling, and our noise has gone up to 171 microvolt RMS. So in the 5 GHz bandwidth, you'll have 170 microvolt noise RMS, which is, again, extremely impressive. So let's go ahead and take a look at an inexpensive oscilloscope like the Rigol DS6104, which is a 1 GHz scope, and also the Tektronix MDO, which is an 8-bit scope, which is a very, very low front end noise as well, and we can do a comparison. Now, why do we care about this number at all? It's because there is no point in having a 10-bit analog to digital converter if your system noise hasn't been adequately scaled back also. Otherwise, you're going to be eating into your quantization levels. You want to make sure the front-end noise of the scope doesn't fill up your LSB at the bottom range of your ATD converter. Otherwise, you're throwing away bits in noise essentially. You can have 100 bits. It wouldn't matter if your noise is going to be overwhelming your quantization noise. So remember those numbers, and let's do two quick measurements to do a comparison. So here's our first quick comparison. We're comparing to the Rigol DS6104. Of course, this scope is not even close to being in the same class, but it gives you an idea of what kind of numbers you can expect from a scope that doesn't have a really low noise front end. So here, I've gone to the lowest vertical resolution I can. I've set everything up to be exactly the same as the other scope. And look at that, the RMS value is 7.1 millivolt. It is 100 times more noisy than the front end of the Keysight scope. So that's to be expected because this scope also costs significantly less. But nonetheless, you can see how important it is to have a low noise front end because you have 100 times more noise within the same bandwidth here on this scope. And here's a comparison with the Tektronix MDO 4000B series, and this is a really impressive low noise front end in itself. It's one of my favorite instruments in the lab here, and you can see right here that the equivalent noise of this in the 1 GHz bandwidth is about 109, 110 microvolt RMS compared to the 85, the 86 we had before. So it's about 20 microvolt RMS more noisy, but again, it doesn't need to be as low noise because it only has an 8-bit A to D converter like a traditional oscilloscope, so it doesn't matter so much. So if I were to go ahead and change the acquisition bandwidth of the Keysight scope to match this noise, I will have a 2 GHz capture bandwidth as opposed to 1 GHz, so it's significantly lower noise density than the front of the MDO. But again, this is an 8-bit ADC, so it doesn't need to, but this illustrates the point really clearly of why it's important to have a low noise front end if you're going to scale up your A to D converters to go with it. So you saw me do a quick noise measurement on the oscilloscope. Now I can go ahead and measure SFDR and ENOB and all those wonderful things as well. But in order to save some time, I'm going to measure those separately and provide them as a plot that accompanies the blog post at a later date. But for now, I just wanted to quickly show you one spurious-free dynamic range measurement. Here I have on the floor a Keysight E8267D, which is a PSG vector signal generator. These are some of the lowest phase noise signal vector generators that are available on the market. This one is a 20 GHz model. Right now I have it set to 4.19 GHz, which is somewhere in the middle of the band and the frequency band that the scope supports. And I'm interested in measuring the spurious-free dynamic range under this condition. So I've done a little quick setup here for us just to do this measurement, and we can move on to doing some other experiments after this. So here we go. I have the scope captured in channel 1 showing you here's our waveform over there. So let's go ahead and adjust the vertical scaling in order to get something that doesn't saturate the ADCs while simultaneously maximizing the full scale inputs. There we go. Oh, here we go at 100 millivolt per division. I'm going to go ahead and increase the power a little bit just so I can cover that remaining gap as well. I think somewhere around here is reasonable. And I've set up the spectrum of the signal, and here's our spectrum. You can see here's a main tone right there. It's being measured at 4.19 gigahertz. Its power is 1.1 dBm, and you can see that I have limited the scope's bandwidth to 5 gigahertz. Let's say you're looking at a 5 gigahertz broadband signal, and you can see all the various spurs that are there. Those spurs are not from the synthesizer, they're from the analog to digital converter and all the DSP processing and every imperfection in the system. And you can see I have placed two markers, one taking the peak of the signal right here, and another one at the very peak of the highest spur. That will be our spurious-free dynamic range, and you can see it says 62.6 dB. So with a 4.2 gigahertz signal, we have a 62.6 dB of spurious-free dynamic range, which is really, really high and really impressive. And you get even more SFDR at around 500 megahertz. The SFDR is more than 70 better than 70 dB, and at 8 GHz is approximately 50 dB. So you have a good SFDR performance from the whole system and not just from the analog to digital converter, and I thought it would be interesting to take a look at that before we move to our main experiments. So here's our first experiment. We're going to characterize a wireless system with an interfering adjacent channel. Now normally a system like this is characterized using a spectrum analyzer, but because of the incredible high dynamic range that the S-Series oscilloscopes from Keysight offers, we can actually do this characterization using the oscilloscope, which is a little bit unusual. So here we have our transmit antenna, here's our receive antenna over here, and this is our interfering source, and our up converter modulator is over there being fed from a Keysight or an Agilent 8030A arbitrary waveform generator plus a Keysight MSO-S to analyze the data. Now this looks a little bit complicated, of course, so I have prepared a block diagram. So let's take a quick look at the block diagram of the system, then we'll go over the setup and do some exciting measurements. So here's the block diagram of the setup that I have prepared. So it's all built around the MAX2721. So I'm interested in characterizing the performance of the system, and I'm feeding the baseband signal to this IQ up converter from an N6050A 15-bit 1.25 gigasample per second arbitrary waveform generator, which is an excellent source itself, and I'm feeding the LO from a Rigol DSG3060 synthesizer. So we have our LO, which is at half rate coming in here. The output of the PA driver is fed into a horn antenna. That horn antenna is then our wireless link and is received from another horn antenna, and the output of that antenna is fed into a programmable attenuator, and then it's fed to a combiner. So the reason I'm using a programmable attenuator is because this allows us to adjust our path loss as we wish without having to separate the antennas any further from each other. So this emulates further transmission attenuation essentially. At the same time, I have a QPSK source which is very close in frequency to the fundamental tone that I'm trying to detect. That's going to be an interfering pattern, and I'm combining the interfering pattern as well as the pattern that I'm interested in, and then feeding it directly into the MSO-S series. So the carrier frequency of the desired link is at 2.5 GHz. It's going to be a 16 QAM constellation, and the QPSK interfering pattern is going to be at 2.44 GHz, and it's going to kind of mix together with that. So the scope, of course, is a broadband instrument, so it's going to capture the entire spectrum from DC all the way up to 8.4 GHz, so you can capture the entire spectrum. So of course it's going to capture both the interference pattern as well as the main signal, and you could have even more things added to it, but this will be a very interesting setup itself. So first we're going to disable the interfering pattern, look at the performance of this, do some measurements with it, and then we're going to do some actual demodulation of the constellation and see how well the MSO-S series will perform, especially in terms of dynamic range and noise floor. So now that you have this, I have a printout of this separately, so let's take a look at the setup a little bit more in detail so we feel comfortable with it, and then we'll do the measurement. So let's take a closer look at the setup. I'm going to try and hold the camera as steady as possible. So here's our modulator that we're interested in characterizing, and the baseband signals to the modulator come from the arbitrary waveform generator that I mentioned. It's also an Agilent product in the PXI format. And here's the S-Series oscilloscope, which we're using channel 1 as the received signal. And if you follow that received signal, you can see that that comes from a combiner. So here we are, we're combining our interfering signal. This is our QPSK generator, so it's feeding in here, and on the other side we have a signal that comes from the unreceived attenuator, and the input of the unreceived attenuator is then connected, of course, to our receive antenna. And on the other side you can see that the output of the PA is connected to our transmit antenna. So the signal is being transmitted from here and being received from this antenna. These are polarizing antennas, quite broadband, so we have no problem from that regard. So there's our overall system. So let's go ahead and power things on one at a time. And also the LO signal, the half rate LO signal, comes from a Rigol DSG3060, which is their new synthesizer. I'll review that in a different video, just using it here to generate our LO signal. So there it is. So now we have a full system going on here, and one of the very first we want to do, power it on, generate a tone, and do some basic measurements in the transmitter before we do demodulation. So now the system is active. I have 88 milliamps going into our modulator. The arbitrary waveform generator is generating 2 tones for us in order to characterize the image rejection and the LO feed through of the transmitter. So here are the 2 tones. You can see 10 megahertz and 12 megahertz right in the middle of the screen. This is the control software that controls the arbitrary waveform generator. Of course, the MSO-S is capturing signal in the time domain, and of the transmitter is transmitting. Here's our transmit horn antenna, and this is the LO signal. You can see a 10 dBm signal at 1.25 gigahertz is being applied, and that's multiplied by 2 in the modulator itself, giving us a 2.5 gigahertz carrier signal. The QPSK generator is turned off, and you can see that it's being fed from the rival power supply, and that is also consuming no current because I haven't enabled the interfering pattern yet. So what we expect to see now is we expect to see our two-tone from up there, modulator around 2.5 gigahertz. This is a double sideband up converter, so you should have good image rejection and so on. So let me get the camera just in the right area here for you guys, and we can go ahead and take a look. Right now the oscilloscope is set to 1 millivolt per division, so of course you're not going to see anything yet. So let's go ahead and change the scale to all the way down to 5. We can even go down. There it is. At we can even go as low as 2 millivolt per division. So this is now a 2 millivolt per division signal. So you can see that it's actually a very, very small signal amplitude. So let's go ahead and do some really basic measurement. Let's take a look at the peak-to-peak signal that we are actually capturing. And if I go under vertical and select the peak-to-peak signal, you can tell me, as you can see, it gives me a little window telling you a little description of what it is that you're about to do. There it is, there are peak-to-peak signal, and it's about 11 millivolt at peak-to-peak and so on. And sometimes it drops to 15 dBm, and that's one thing I haven't mentioned, is that the antennas that I'm using are of course going to pick up other sources of noise that are available in the room. So occasionally a packet, a Wi-Fi packet or a wireless mouse packet or so is captured also by the antenna, and you can see the little increase in the amplitude because the scope is capturing everything all the way from DC all the way up to 8.4 gigahertz right now. So it's going to capture a whole bunch of other things that I don't want. This is not the interfering pattern that I intend to inject myself. This is just from the stuff that's available in the room. But anyhow, we can ignore that because it's just outside of the frequency we're going to look at. So you can see the signal is really small. So let's go and delete this. We're not going to look at this anymore. And let's go and add an FFD so that we can look at the proper intermodulation products as well as the LO rejection that we want to characterize for this transmitter. And that's really easy to do. We go under Math, under Function, and here you can see a complete list of all the functions you can apply on this oscilloscope. And there's quite an extensive list of things you can do, as well as various types of filters and so on, which we will get to later. So under that, I'm going to go ahead under category of FFD. I'm going to choose FFD magnitude, pretty straightforward. Our window is going to be a flat top window, and I'm going to increase the maximum peak count to 10. This maximum peak count is the number of peak values the scope will report if you ask it to measure the peak amplitudes that are available in the spectrum. Basically just like a spectrum analyzer, that's what you would ultimately want to see from a properly implemented FFD function. I'm going to go ahead and turn it on, and as soon as I do that, the scope is going to give me another window at the bottom, which is my FFD window, which is right now right underneath this this call-out window here, and you can make these transparent, and you can set the transparency and so on in the settings. Right now I have it completely opaque because I don't want it's easier to film it this way, but you can have transparency so you can see what's happening to the waveform right underneath this. So let's go ahead and set our center frequency to 2.5 gigahertz because that's the center frequency we want to take a look at. And our span is going to be about 50 megahertz is enough because our IFs are at 10 and 12, so that's going to be perfect. Here's our 50 megahertz, and I'm going to set the resolution bandwidth to something small, something like 100 kilohertz. And you can note right away that the interface here is of a spectrum analyzer because you want the scope to take care of all the sampling and all the memory and everything by itself, and for you not to worry about that, you want to just tell it what it is that you're interested in seeing, and the scope will do the rest for you. I'm going to set the reference level to minus 80 dBm, and this is going to give us a good view of our spectrum right away. So let's go ahead and close this. And there we go, we get rid of this. And here's our spectrum at the bottom really nicely. And at the same time, we can see the time domain signal at the top. And if you look closely, you can see occasionally the amplitude gets bigger and smaller. Those are the packets that I was referring to before. So all of our tones are here. But of course, sometimes you want to look at the spectrum by itself. It's not a problem. We go under Setup and under Display. And now we can go ahead and change the way the windows are stacked. You can tell them to stack them vertically, you can stack them horizontally, or you can tell them that you're interested in a tabbed view, like a browser essentially. So I'm going to go ahead and say give me a tabbed view of this, And now I have two tabs. I have a spectrum tab here, and I have a time domain tab here, and now I can go back and forth between them. And because this is a Windows 7 machine and this software is running in a Windows environment, you can actually grab this tab and put it on a different display, drag it onto a different display. You can have two different monitors now side by side showing you spectrum and time domain, which is really, really handy when you have multiple displays. Right now, the other display I have is being used for the arbitrary waveform generator, so I'm going to keep it here. Now let's do some measurements on this, and I'm going to go ahead and say, well, mark the peaks for me. As soon as I tell it to do that, I have to tell it what reference level for the peaks it wants to use. I can just drag that reference up, up and down here, so I can just put the reference here, for example, or you can enter a desired value. I can say put it at minus 82 dBm, for example. There it is, roughly around here. So any peak that's above minus 82 dBm will get marked up. As you can see these little dots that appear here, and a whole table at the bottom showing you all the values of all the peaks of the signals are listed out, which is really, really handy and very nice. Now, sometimes you don't want to look back and forth between this and the waveform. You can go ahead and change that. You can go under Setup and Display, and under Callouts, you can say, give me the FFD callouts. And I really like this function because it now gives me these little windows, and I can put these little windows right next to the peaks, and they are marked with a little callout line, so that makes it really, really easy for me to grab them and put them where they belong. There we go, perfect. Now I can characterize the wireless link really easily. So what do we have on the display? So I have our two IF tones that are up converted. There you go, sitting at these two frequencies right there. Here's my third order intermodulation products due to the nonlinearities of the transmitter itself. Here's my LO leakage sitting right in the middle. Here's the image of the signal, which ideally should not be there at all. And here's the second harmonic of the IF signals, mostly due to IF nonlinearity. So now I have all of the tones here. And if I look here, the difference between the fundamental tone and the third intermodulation products is about 30 dB, which is not very much, especially if you want to use complex modulation schemes. So let's go ahead and reduce the output power of the PA in order to reduce the intermodulation products and get a little bit of a better result before we finalize it. So let's go ahead here, and I have a little screwdriver. I can adjust the Vga gain from the board. I'm not going to show it to you on there so you can look at this live. There you go. See, I'm decreasing the power. The third order intermodulation products are of course going to go down by 3 times faster. So let's go ahead until we have about, let's say about 35 or maybe even 40. There we go. Maybe stop around here. There we go. Now we have much more reasonable. It's a little bit better. It's now 35 dB, 35 dB of rejection. You can see our image also gone down significantly, and the second order harmonics are now actually below our reference level, so we lost that little call out that was there. The LO leakage is going to of course remain fairly constant. It's going to go directly down perhaps a little bit from the gain of the PA. And we should note that we're looking at signals that are minus 80, minus 85 dBm in amplitude. This is not a spectrum analysis, this is an oscilloscope, and it's quite incredible that you can look at signals and look at how much these signals are already above the noise floor, given how much bandwidth we have. We're capturing 8.4 gigahertz of bandwidth simultaneously, but we can easily measure tones that are minus 95 dBm in amplitude without any problems. And what is really important here is that I want to emphasize the dynamic range capability of the instrument. So the next step now would be, because we are happy with the IM3 modulation after the adjustment, for example, we can go ahead and switch now to a QAM constellation and be able to use a demodulation software like the VSA from Keysight and do a complete constellation measurement. And we can change the input power, and we can introduce the interferer, and we can again further push the scope performance to the edges of what it can do, and we can see what to expect from such a large dynamic range instrument. So let's go and change the type of signal we're applying. If I go up there again, sorry for the camera angle, I just want to show you what it is that I'm applying. There it is. I'm going to apply 16 QAM signal, which is at about 10 megabaud, which is about 40 megabits per second. It's a reasonably narrow bandwidth signal for our purposes. So I'm going to go ahead and click on download right here. And there we go. And that's going to download that into the instrument. And if I go back here, it should show up in just a second. There it is. There's our QAM constellation, nice and straightforward. Let me just make sure I get this camera adjusted. There it is. Now you can see from here, this is the main component of the spectrum which carries the 16 QAM constellation. You can see the third order intermodulation products are creating side lobes there, which are undesired, so this is going to hurt the adjacent channel power ratings and so on. But nonetheless, this is we were expecting to see some power outside of the channel, because we saw that the intermodulation products were only minus 35 dB below the fundamental. So this is to be expected. Now what can we do with this? Well, I can go ahead and try and demodulate it. Now, in order for you to be able to demodulate this signal, you can either capture it and then process it in MATLAB or so on, or you can have the scope remotely connected to a demodulation software. And of course, this is a Windows machine, so we can go ahead and run VSA, which is the Keysight's vector signal analysis software. A very powerful tool that you can run. Now, because this runs directly on the scope, it's going to be really fast because it grabs the data directly from the scope's acquisition board, so it's going to be pretty quick. And it's going to be launched, and it will set the scope for us. I've already configured it, so it'll be pretty straightforward for us to go and take a look. There we go. There it is. And I've already done everything for us, so we can see. Here's the spectrum we were looking at before, and you can see there again the tones right outside of the main spectrum you are interested to take a look at. And here is our constellation, a 16 QAM constellation. We can go ahead and auto scale, just so that make sure that the scope has the proper auto scaling. Remember, the oscilloscope software is still running in the background. Here we go. Now it's fully controlled by the VSA, so it says, you know, exit the 89600 is the part number for the VSA software, and even in here you can see a little bit of the interference that sometimes appears and disappears. So now it's completely controlled by the other software. Again, it's running at 20 gigasample per second with 8.4 gigahertz of bandwidth, so everything is exactly the same as before. And we are having all of our demodulation. And if I go back, look at the scale. So the scale is sitting at 2 millivolts per division still. So it's the same scale as before, same signal power. And here I have set up two markers. This marker here, marker number 1, is measuring the power in the band. So this is minus 43 dBm. So the scope is demodulating a 16 QAM constellation that has a total power of minus 43 dBm. And if you think that's impressive, we can go ahead and reduce it even further with the external attenuator. So I'm going to go ahead and make it 10 dB smaller. Look at that. Now it's sitting at about minus 50. I can auto scale it again to make sure the scope has this, sitting at the most efficient vertical scaling. I can go ahead and make it 10 dB smaller still. There we go. Now it's sitting at minus 62. Make sure it is still auto scale. Now if I go back, you can see the scaling is at 1 millivolt per division. So this is as small of a scaling as you can get. This is where the signal is sitting. The signal is only just over 2 millivolt peak to peak. That's how small the signal is. And in that signal, sitting at 2.5 gigahertz, it carries a QAM constellation that the scope is demodulating. This is minus 63 dBm. Let's go ahead even further. Minus 68 dBm. How about a little bit more? Let me see where it will break up, where you cannot demodulate anymore. No, still can do it. Somewhere around here. Maybe a little bit more. There you go. No, it seems like I can go even further. There you go. That's around here. And around here, you no longer can. It's starting to break up, and you cannot capture the 16 QAM constellation. So I challenge you to go and find a scope on the market that can demodulate a minus 73 dBm power signal at 2.5 gigahertz carrier with the 16 QAM constellation. This is an amazing result. You know, I praise it only because I've never seen an oscilloscope do something like this with such a tiny signal power, because it has such a low noise front end. So you can see this is right at the edge, but if I were to simplify the constellation, I can go even lower in power. So instead of 16 QAM, let's go ahead and choose QPSK. Now I'm going to change. Now I'm changing the constellation to a QPSK, and it's going to get downloaded. There it is, and I'm going to tell the software that this is a QPSK constellation. So now it's going to change the constellation for us. There we go. So you can see that because the constellation is so much simpler, the required signal to noise ratio is much more relaxed. So now we can demodulate this signal much easier. So I can go even lower in power. Let's go ahead by another couple of dBm. Still okay. Yeah, we're still okay. There you go. Around here it's beginning to break apart. It's having trouble detecting that, so let me give it a little bit less attenuation. There you go. So now this is a minus 76 dBm. So a QPSK signal at a 2.5 GHz carrier, total power of the QPSK signal is minus 76 dBm, and we can still demodulate that. That's a really impressive and interesting result. So let's go back to our 16 QAM again, like we had before. Here's, I'm going to download the 16 QAM back in here, and I'm going to go ahead back in here and tell the instrument to demodulate our 16 QAM signal. There we go. I'm going to increase the power back to 0. I'm going to auto scale it. Now we can go ahead and add our interference pattern. So in order to do that, we're going to go ahead and turn on our other board, and I'm going to configure it to generate a QPSK signal. There we go. And we're going to go back to the scope and take a look here. And you will see why this is an important test in just a moment. Here we go. So now we have two signals present at the same time. Here's our interfering signal, which is quite large compared to the signal we're trying to demodulate. So the scope is still continues to demodulate the 16 QAM constellation signal. Right now the interfering pattern's power is minus 14 dBm. So this is a minus 14 dBm total power channel. And next to us we're at minus 43 dBm again. So what is important here is that these signals are captured simultaneously. So as a result, if you look at the scope can no longer sit at 2 millivolt per division. Now it's sitting at 32 millivolt per division. And this is important because when the scope is sitting at 32 millivolt per division, the signal of interest is sitting right down there. Everything else is essentially interfering that you don't want to have. This is what a large dynamic range instrument should be able to do. Should be able to capture simultaneously both of those and still demodulate that. So let's go and push it now and see how far we can continue to push it when there is a large interfering signal present. Remember that I can no longer auto scale it because it wouldn't matter, because it's dominated by this power. I can no longer reduce the scale of the oscilloscope to below minus 32. So let's go ahead and increase the power by another 10 dBm. You can see that the signal integrity has become a little bit worse because it's now closer to the noise floor. Now we're at minus 50 dBm. Let's go another 5. Still fine. We can still demodulate that. Let's go another 3 or so. There we go. We are right now sitting at around the edge of what we can do. Again, if I auto scale, it wouldn't matter because our interfering signal is still occupying almost all of this power. I'm going to go ahead and just briefly turn off the interfering signal so you can see the difference. If I turn off the interfering signal, you can see that is where our signal is sitting in. That's what the scope is looking at. At this scale, this is the signal of interest. And it's important because if you don't have a good high resolution ADC, if you don't have a good low noise front end, there is nothing for you to detect in that region. So I'm going to go ahead and turn the interference signal back on. There it is. And here you go. I'm going to do the same thing in the spectrum domain. There you go. I'm going to turn the interference signal off. You can see that this will disappear, but this will remain the same. Look, there is no change at all in the demodulation. I'm going to turn it back on. Look at that. Now, just to put it into perspective, the difference between the power of the signal of interest, which is minus 58 dBm, to the interferer, which is minus 14 dBm, is 44 dB. So there is 44 dB more power in this band than it is in this band. That's a factor of 26,000. So there is 26,000 times more power in the interfering signal than the QAM constellation that we are demodulating. This would be like trying to listen to someone whisper across the street when there's two people screaming in your ear right next to you. And the only way you can do this is if you have a crazy amount of dynamic range and high resolution to be able to capture a tiny signal at the bottom close to your noise floor, and at the same time capture this signal. So because I'm capturing both of these, I can demodulate these simultaneously as I'm demodulating this. And there can be even more interfering signals, and then you have to adjust the scales appropriately at that time. But here's an example of two of them side by side. And I hope that this demonstrates, this whole experiment demonstrates what the importance is of having this type of dynamic range. So you can look at your signal, your RF radio signal, directly on your oscilloscope without even needing to have any amplification because it is so low noise. Now this doesn't limit us, of course, to only look at the RF signal. We are also free to look at our baseband signal at the same time. So I can occupy channel 1 with my RF signal and channel 2 and channel 4 with my IF signal, and have a complete radio characterization unit at my disposal, all in one instrument. Anywhere from DC to 8.4 gigahertz, I can do simultaneously. I don't need to even disconnect and connect it to spectrum analyzer. I would only need to do that under situations where I need even more dynamic range, which can happen, of course. At some point, the dynamic range of a spectrum analyzer is going to beat the dynamic range of the oscilloscope. But here you have the flexibility of being able to do some quick measurements and perhaps capture and have almost everything you want to do except for some niche points directly on here. So just as a last thing for completion, let's go ahead and take the baseband signals from here and directly connect them to the oscilloscope and see what kind of demodulation we can get and how far we can push the EVM constellation performance of the instrument just by looking at the baseband signal alone. And just to demonstrate the instrument's capability to capture baseband signals as well, which of course you should have no problems with, it will use two channels, one for I and one for Q. Here I'm pushing my ARP to its maximum limit. Is pretty much, I'm doing 625 megabaud. That's 2 samples because it has a sample rate of 1.25 gigasample per second, and it's a 256 QAM signal. So that's equivalent to 5 gigabit per second of wireless data, for example, in a wireless system. So now if you go ahead and take a look once again at the instrument, we can see that we are demodulating that signal without any difficulty. Here's our 256 QAM constellation. I'll show you a closer view of that, and we are demodulating a span of 1.5 gigahertz here, and you can see that the EVM is about 0.5% with an SNR of 40 dB. Now that's really good, particularly because this is a single-ended measurement essentially, because I'm only using channel 2 and channel 4. I'm terminating the other 2 outputs. So all the other second order modulation products, all the second order harmonics, for example, are not cancelled because I'm not subtracting them. So this is again another test showing not just how good the scope is, but also how good the arbitrary waveform generator is, also from Agilent. And we can take a closer look at this constellation just so we can have a better look at it, and I can go ahead and change the view to be a single, and there it is. Here are a constellation. I can zoom in so you can really see the dots. There they are. Look at that. It looks almost ideal. Of course it's not. It's generated live, and look how fast the update rate is. I mean, this thing is not just it's capturing it, it's demodulating it, it's equalizing it, and it's doing all the computation at 4096 symbols, incredibly fast, again because it's running on the instrument and because of the really fast computer that's on board this oscilloscope. We are able to do this. So I think that should be good for our wireless experiments. Now we can go ahead and try some broadband experiments, which will be very different. This way you can see the capability of the scope in 2 really different types of applications. So here's the setup for our next experiment. We're going to do a couple of different things. We'll be primarily looking at backplane communication challenges, and for the first experiment we're going to look at this PRBS pattern generator, which is going to generate an 8 gigabit per second signal for us. I'm going to use the MSO-S Series oscilloscope to do jitter decomposition and take a look at the eye quality and do some CDR and recovery directly on the oscilloscope itself. And once we have a fairly good idea of how to do that, we're going to move on to one of a somewhat more complex experiment. Here I have another PRBS pattern generator, and I actually have a particular backplane channel there. Over at the back there's a Tyco backplane, and it's a 30-inch differential link on there, which is going to have quite a bit of attenuation at the baud rate, so it's going to have quite a bit of ISI. So we're going to go ahead and not just look at the signal, but we're going to also use the oscilloscope's capability to do live equalization, apply a particular filter, and then finally take those coefficients and use pre-emphasis in order to correctly be able to establish a link despite the fact that it has so much ISI. So by using the oscilloscope's built-in software and of course this high bandwidth, we should be able to do quite a bit of analysis on these type of systems. So let's get started. So here we have our serial I/O board. This is actually an Agilent product itself. On the other side of this board there is an FPGA which generates different types of PRBS signals with various amplitudes and so on. It has multiple output channels. For our purposes we're using just one of the output channels, and currently I have it set to 6 gigabit per second. So it's generating a PRBS sequence at 6 gigabit per second. I have no idea what the I quality is, and that's what I'm interested to find out. I want to find out the properties like the different types of jitter that are present on the PRBS signal, and what kind of bandwidth it has, what kind of I quality it has, and I want to do all these measurements directly on the scope. Now here at the output I'm taking both the positive and the negative output, and if you look, I'm feeding them to channel 1 and channel 3 of the MSO-S Series scope. Now another nice feature of the scope is that the scope will do for you a proper hardware differential signal. So it's not doing it by the signals that are processed afterwards. So it doesn't do subtraction between two channels. In software it does it actually in hardware. So it's processed essentially in real time. There is no delay, and it doesn't have any effect on the speed in which it operates, which is really nice. So at the same time, because it's done in hardware, you can also get the common mode signal, which we're not really interested in. We're only going to look at the differential signal. So let's go ahead and take a look at setting that up and getting ourselves some measurements. So first thing I'm going to do is I'm going to go under the channel properties, and here you can see there is an option to do a differential between channels 1 to 3. I'm going to enable that, and as soon as I do that, now this shown waveform is channel 1 minus channel 3, and I can also have channel 1 plus channel 3 divided by 2, which is a common mode signal. So we're not going to look at that for now. We're going to just look at the subtraction, the differential signal between the two channels. There it is. So it's now the differential signal between the two channels. I'm going to go ahead and enable the pattern, and here's our pattern. So let's go ahead and adjust amplitude a little bit so we can get a better look at it. And here's our pattern. Of course, that's what you expect to see when you do a rising edge trigger. So let's just go and change the trigger as well, just for sake of completeness and make it a little bit easier to look at. Let's go and make it cross. There it is. So you can kind of already see our serial data in place. So first step, let's make an eye diagram. Now the scope can do for us, of course, clock and data recovery. So we're going to take advantage of that and get the scope to do that. Let me turn this light off. There we go. So let's go under analysis, and under analyze we can go ahead and select clock recovery. Very good. So here we have our clock recovery options. The scope is equipped with setup wizards for every single type of analysis it can do. So you can just walk through the wizard and it will tell you how to set it up, what values to set up, and how to do a different kind of configuration for you to get an optimal measurement. So we're going to set it up ourselves. You can go through the wizard too, but it's just more interesting to set it up. So first thing is, let's set the thresholds up. This is where you tell the scope how to distinguish various levels of logic, for example. So here we're going to say that let the threshold be 0, because you can see this is an AC coupled signal, so the threshold is at 0. Let's give it a hysteresis of about 50 millivolt. This should be good enough for our purposes. There's that. And in terms of clock recovery, I'm going to set it to fully automatic. It's going to figure it out by itself. It's going to figure out the data rate, the data pattern, everything is going to be fully automatic. I don't have to worry about any of that. So I'm going to tell it, there we go, put the clock for us, and now it's showing the clock, recovered clock, and we'll take a look at that and give me a real-time eye diagram. There it is. Check this out. So here's our complete measurement. Here's our eye diagram. You can see, and it's continuously building waveforms, and this is a color gradient waveform. I hope it shows up well on the display. But you can see the different regions that are the brighter are the regions where there is a highest occurrence of that waveform in that particular location. So you can see a typical eye diagram being built right now, and there are no lines through the middle of the eye diagram, so this is an error-free transmission, at least reasonably good error-free transmission. We'll have to do an analysis to make sure exactly what is going on. Let's also go ahead and under acquisition, and let's increase the depth of the memory so we can have more data. Since this scope can have 400 million points per channel, we don't need that much, of course. Let's just go ahead and maybe capture something like, I don't know, 500,000 points. That should be good enough for our purposes. So of course the scope now has to process all that data, so the update rate is going to go down, and this is because there's a heavy amount of computation going on. It's doing for us clock and data recovery live, of course. Now that we have this, we can take it a step further, and we can actually go ahead and look at jitter decomposition. Jitter decomposition suite is a different analysis tool, so which is also available here. EasyJit Complete is the name of the software suite. There we go. So we can launch that, and here we can do jitter decomposition as well as noise analysis. Again, it has a setup wizard. You can go through the wizard, and it's going to take you step by step and tell you how to set it up. We don't need that. We're going to do it ourselves. The thresholds are already set up from before. The clock recovery is already set up from before. All I'm going to do is go ahead and enable it. So now it's going to open a whole new window at the bottom, and since now because we're getting a little bit crowded, I'm going to move that window into a new location like we did before, and that's pretty straightforward. We're going to say give me a tabbed window, and it's going to separate it for us. So let's go back here for just a second. So we have at the same time our clock and data recovery, our eye diagram, and our jitter and noise analysis on this window, and I'm going to go ahead and enable everything, so we can have a good look at what is going on. And let me get this just right for us. There we go. So there's a lot of information here, so let's take a look and see what we're looking at. At the bottom we have our analysis report. So it's telling us that the data rate is 5.997 so on gigabit per second, which is correct. That's what it should be. The pattern length is 127. This is a 2 to the 7 minus 1 PRBS sequence. That's correct. Now this is all the interesting information that comes out of analyzing the waveform in real time and telling us information about the source of jitter and how it will affect the signal. So the total jitter is telling us for the 1e to the minus 12 bit error rate is about 57 picosecond, and it gives us random jitter, data dependent jitter, duty cycle distortion, and ISI that's contributing to the total amount of jitter. So immediately I can tell that this is a reasonably good eye diagram, because the ISI contribution peak to the total jitter is not that much, and that is obvious because if I look at the eye diagram here, I can see the eye diagram is not too bad. It's not, doesn't have too much of an ISI influence on it. So that's pretty useful. And if I go back again over here, I can also look at each of these individual windows, which are constantly being updated with the information I'm looking for. For example, this window, by double clicking, I get a complete view of it. It's showing me the total jitter, the random jitter, and the data dependent jitter. And you can see that the random jitter is the most dominant aspect of this jitter. The data dependent jitter is actually quite small, and that is again because the ISI is fairly limited. So let's go ahead again and look at some more of these waveforms, because there's one other thing that I'm interested in showing you. There it is. This is the one I wanted to see. This is also really useful. This is telling us the individual bits in our 126 bit pattern, and it's overlapping on top of that the amount of data dependent jitter. So you can find here at this point where the highest amount of jitter occurs, and it makes sense that it occurs in a consecutive 1 and 0 pattern. So you can immediately find out at what point in your pattern you have the worst jitter contribution because of data dependent jitter, because of ISI. This of course will grow as necessary depending on how many bits are going to be available in the pattern that you're trying to measure. But the main point is that all of these measurements are available to you, and you can look at each individual one. Here's a bathtub curve, for example. You can see the bathtub curve is being continuously built. So the blue curve at the bottom is the extrapolation, and the measurement is going to continue to grow depending on how much memory you have selected. So you can see how much of it is exact measurement and how much of it is extrapolation based on a particular model. So all of these different measurements are part of the easy jitter analysis, the complete analysis toolkit, which is going to help you, detect the different kinds of problems in your eye diagrams and find out every bit of information you'd want to know about its jitter composition. And on top of that, you can go ahead and enable the noise measurement as well and create your slice that you're interested in. Particularly here in this case, I have the slice in the middle of the eye. That's going to give you a whole bunch of other information in terms of the eye amplitude, the eye quality, the eye height, the type of noise you have on your zeros and the type of noise you have on your ones. So if you have a pattern, for example, that continuously causes problems whenever a 0 is transmitted as opposed to a 1, you can take a correlation of that and be able to do all these measurements. I'm not going to go through too much of a detail, but when you enable the noise, you're going to get a whole bunch of extra measurements. You can see all of these. Again, I can spend hours and hours talking about each of these with you, but it should hopefully give you a good idea of all the capabilities that are built into the scope in order to do a complete noise and jitter analysis using the toolkit that's built into it, as well as of course the CDR that's in there. So the next thing I want to do is I want to take all these capabilities, and on top of this we can also do equalization. So let's go look at a proper channel and see what the equalization software can do for us. So here's the setup for our backplane experiment. So this FPGA currently has 2 active transceivers. One of the transceivers has a simple loopback through these blue cables. So there is no ISI and there is no bandwidth limitation. As a result, it's a simple link can be established without any errors. The other link, however, is taken from the output of the transmitters, goes into a Tyco backplane, which is a 30-inch of PCB trace, which is going to have quite a bit of bandwidth limitation, and the output is then taken and fed back to the receivers on the board. Now unfortunately, because of the ISI limitation of this at 3.125 gigabit per second, we are not able to establish a link at all, and the link is not successful. And because of that, we want to investigate, well, what does the eye diagram look like at the output? What kind of equalization is required? Why is this link failing? And if you want to answer those questions, you have to have the necessary tools to measure your eye diagram and find out all that information. And for that purpose, I'm not going to use the differential signal into the scope anymore. I'm going to use a differential probe. So directly connecting the 2 signals in here, and this allows us to do a differential measurement only using one of the channels of the oscilloscope. That's just a different way I want to show you one of the probes that are available. So let me quickly show you the software as well. I'm going to try and not shake this camera too much here. So here's the software that is running on the FPGA board, and you can see there's 2 links active. At the very top, you can see a link that has a 3.125 megabit per second, and you can see the bit error rate is 0, so the link is completely error free. At the bottom, you can see that there is no received frames, and the link is continuously failing and is not able to establish any connection, and that's because of the ISI problem I mentioned earlier. So let's go ahead and hook this up directly to the oscilloscope. I'm going to disconnect the received signals from the FPGA board and connect them directly to the probe, and let's take a look and see what's coming out of the signal. Here we go. So the connection is now made. The output is directly connected to the differential probe, and let's take a look at this scope. And whoa, look at that! That is not a pretty signal. So let me focus the camera and then take a look at it. Well, look at that. This signal is riddled with ISI. No wonder the link cannot be established. Let me do a single capture just for a second. Look at that. Look at this. This is the eye crossing we have here. I mean, that's impossible to detect for any reasonable system. So this is, of course, all because of ISI, because of the bandwidth limitation of the trace. So let's go ahead and try and do some of our analysis we did before. It's not going to be very easy to do a proper CDR on this, and the reason for that is because it does have such a poor ISI itself, but I can try and apply equalization to it. So first, let's just go ahead, even though it's not going to work very well, and let's do an eye diagram on this anyway. Let me increase the captured memory. Let's do another 512 million points again, and then let's go ahead under the display and enable our real-time eye diagram. There we go. And in there we can, everything is fine. Let's give it a proper threshold just like we did before. This time I'm going to give it only a 10 millivolt hysteresis, so that's not going to look very pretty. There you go. You can see the eye is basically completely closed. It's unusable, and this is why you're not able to receive the signal on the other side with the FPGA's receivers. Now we can go ahead and try to apply some equalization. So we go under Analyze and under Equalization, and we have a whole bunch of different options. We can do FFE, which is feed-forward equalization, CTLE, continuous time linear equalization, or we can even do DFE, and you can see there's a decision feedback equalization and even advanced forms of it to have even more complex configuration. But for this one, why don't we try and just follow the setup wizard just for fun, just so we can see what that one looks like as well. If I click on the setup wizard, then this display comes on and it gives me a little information about how to set it up. So let's just go step by step. So it's telling us first, well, what kind of equalization do you want to do? Well, I have a whole bunch of different options here. What I can do is I can do a FFE followed by a clock recovery, so you can see a simple block diagram of the different kinds of ways the scope can deal with the way the equalization is applied, because you can apply equalization without clock and data recovery, or you can have your clock and data recovery within the loop and have both. You can say display the waveform with no equalization, FFE only used for clock recovery. So you can see what happens if you have equalization for clock recovery, what happens if you have it for the signal and not for the clock recovery. So all the different kind of combinations, which is important and useful for system characterization. So I want to do my clock recovery and I want to see my waveform after FFE has been applied. So I'm going to select this option. And it says, do you want to show the signal before that? Yeah, I would like to see what it looks like also before equalization. So we'll have two grids on there. Perfect. And it's asking what type of clock recovery method you want to use. There's all these different possibilities. We're going to go with constant frequency. And I'm going to help a little bit just to show you what another option. Instead of a fully automatic baud rate detection, because the ISI is really bad, let's go semi-automatic, and I'm going to give it a hint so it has a starting point. Oops, I made a mistake there. So it has the starting point of starting an analysis. So 3.125 gigabit per second. Perfect. Next. And it's going to tell me that okay, it tried to auto-detect the hysteresis and the threshold level. I'm going to keep whatever it suggested. It's fine with me. And I'm going to increase the amount of memory. Again, let's go for 524 kilo points, 1,000 points. And then finally, just give us a FFE type of, what type of FFE do I want to apply, how many taps do I want, how many precursor taps, how many postcursor taps. So because this is a heavy equalization, let's give it 8 taps and let's give it up to 4 precursor taps. So now a lot of equalization can be applied here, and I'm going to allow it to select its own bandwidth and its own tap delay to make sure that it uses, whether it's a full baud rate taps or half baud rate taps. I'm going to allow it to do it automatically just to show you how easy it is for this system to be put together. And next, and finish, and it's now going to show us what it's capable of doing. And I'm going to also allow it, tell it to give me some auto selection on the taps. I'm going to tell it, find the equalization coefficients for me. I don't have to do it myself. And there we go. It did all of that. And check this out. Here's the eye diagram at the input of the system. Here's the eye diagram at the output of the system. So the oscilloscope not only does clock recovery, but it also has applied our feed-forward equalization, and it looks really nice. And you can see that it has completely opened up the eye. And now this eye, if you were to apply those coefficient patterns directly to, I'll take a single capture here. If you were to apply those coefficient patterns to your system, you should be able to go from here to here in terms of equalization. This is a really nice view to tell you what kind of power the equalization can have in your system. And here I'm also applying on top of this, you can see the signal before and after equalization. The green line is before equalization and the yellow is after. So you can clearly see how the small pulses due to ISI have been amplified because of the tap spacing and the tap coefficients. And again, you can go ahead under the utility equalization and you can take a look at the taps themselves and take note of these taps and go ahead and apply those in any other software you have, or apply them in hardware in order to have the equalization directly applied to your link. So it should be pretty straightforward. Now, since I have an idea about the taps, I can go ahead and enter my peaking filter requirements into the FPGA's transmitter, and by applying that I should be able to open the eye before equalization now that I have some idea of what kind of coefficients I need to apply. Alright, I'm going to enter the coefficients in the FPGA and I'm going to try and see what happens if we can open that eye ourselves. There we go, there it is. Now you can see I applied the coefficients and now the eye diagram has already opened up. And this eye diagram now at the top is now over equalized, even beyond what is necessary. You can clearly see it. You can see exactly what I mean, that all the sharp rising edges are now exaggerated. There's too much overshoot because of the fact that it's over equalized. And now I can go back there and I can go under tap setting and I can tell it to, well, rerun the equalization coefficients for me, and now I will reduce that. And now I'm back to the two normal signals, and you can see that even the quality of this eye is even not as good as this one. But look, now before and after equalization, they have now collapsed on top of each other. So by using this tool, I found out I have ISI. I can characterize and find out exactly what my jitter composition is. I can do a clock and data recovery. I can apply equalization filter. I can get all the equalization coefficients, take those back, put it back in the circuit in hardware, and get the equalization done and open the eye. Now if I were to connect it back, I should be able to have a good link. So let's try it out. Here we go. I disconnected and connect the link back, and let's take a look at our statistics again. Sorry about the camera shake here. Here we go, look at this. Now we have two links that are both functional, and one of them is going through the backplane. So by applying the equalization parameters that I found from the information the oscilloscope provides, I can then go ahead and correct the link and then do the proper equalization. This was just an FFE. I could of course also apply a DFE and all the other fancy things. And there's a whole bunch of software suites available in the scope itself, which you can use to analyze common industry standard protocols, and all of those are available here. I'm not going to go through in this one, but you can see that under analysis I have all these automated test apps for a whole bunch of different types of protocols, including DDRs and Ethernets and a whole bunch of different things you would want, including USB and so on. So of course these softwares you have to pay for individual ones, but they're all available here so we can play with them. But just to give you an idea, just a basic link, this should have given us a good impression of what a complete solution you can get directly in one instrument. Well, I hope that you enjoyed this review, teardown, and experiments with the Keysight MSO-S Series oscilloscope. There was a lot that I wanted to say, so sometimes I had to rush over a few things. Of course, there's no way I can cover everything that this scope can do, but I hope it gave you a good impression of its capabilities, of its performance, and the different type of application that it supports. Now, I only have one request from you. If you like the video, give it a thumbs up, leave a comment, and if you do happen to purchase one of these oscilloscopes because you saw the review, let them know that you saw the review on the signal path. It will always help me have a good relationship with the manufacturer. And I will also continue to do more videos using this scope in different kind of scenarios in other future videos, and I'm sure you'll be able to enjoy. So make sure you check them out. Until next time.